Today we're going to talk about simplifying radicals. And a radical expression is something that goes under a square root sign. All right? So this thing is called a radical. So if you had something like the square root of 36, that's called a radical. Okay? A radical expression. Who knows what the square root of 36 means? It is 6. And that says what number times itself gives you 36. And you have a function button on your calculator that will compute square roots for you. Okay? So in this case, so when we simplify a radical, here we go. Square root of, that would be considered simplifying this radical. Okay? How would I simplify the radical square root of 100? What's that equal to? 10, right? Okay. Now, when you simplify radicals, you look for square roots that are inside the radical. But first you have to understand a property of radicals. And one property of radicals is that the square root of a times the square root of b is equal to the square root of a times b. Okay? For instance, let me give you a specific case. Say I have the square root of 900. What two square roots are in the square root of 900? What two numbers are in there? What do you know is in it? What can I divide into 900? 9 and what else? 9 times what? 9 times 10 times 100. Okay? What's the square root of 9? 3. And what's the square root of 100? 10. And what's 3 times 10? 8?
30.
Oh, I thought you said 8. 30. Okay? So I can break it apart into separate square roots, or I could just say that 30 times 30 gives you 900, right? The square root of 900 is 30. Okay? So this square root of 900 is 30, but I could also break it into two perfect squares, 30 or 9 and 100, and then take them outside of the square roots and multiply them together. And either way, I get the same answer. Okay? So what you're doing when you're simplifying radicals, though, is you're pulling out all the perfect square numbers. So here are all the perfect square numbers. 4 is a perfect square number. The next perfect square number is 9. Who can tell me the next perfect square number? This is 2 squared, right? This is 3 squared. What's the next perfect square number? Sarah?
16.
16. What's after that?
25.
25. 36. What's after 36? 7 times 7. 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. Did you know that 11? Who knows 11 times 11? 121. I bet you know 12 times 12. 144. I guess we could go all the way up to 13 times 13, 169. So if you know these things, that's good. Okay? So when you're simplifying radicals, what you're trying to do is pull out these numbers using this property that you can pull out. You can separate this out within the square roots, and you're trying to pull them out of the square roots. Okay? For instance, say I have the square root of 54. What perfect square number is there in 54? Anyone know? Hello. This is for Catherine Huntington. Not during class. Okay? What perfect square number is in 54? 7? What perfect square number? What times what gives you 54? 6 and what? 6 times 9. Okay? So what you're looking for is numbers inside that square root sign that are perfect squares. So one of those is a 9, okay? And one of those is a 6. Well, you say 6 isn't a perfect square number. That's okay, okay? Because you want it, that just stays inside the square root. What is the square root of 9? What's the square root of 9? 3. So you can rewrite the square root of 54 as 3 times the square root of 6, okay? And you might say, why the heck would I want to do that? Why don't I just leave it as the square root of 54, right? And the reason for that is A, it enables you to see relationships when you're doing like the Pythagorean theorem, when you're looking at different triangles. It enables you to see patterns with square roots and stuff. It also is easier, like when we didn't have calculators in school, it's easier to figure out about what that number is, okay? Because I know that the square root of 6 has got to be 2 point something, and 3 times 2 point something is going to be, I don't know, about 7 point something, somewhere in there. And so you can kind of estimate how big that number is by pulling things out of square roots, okay? So let's try another one, okay? So let's try the square root of 50. What perfect square number is in square root of 50? You can do it. What perfect square number is in the square root of 50? 2 times what? 25, right? So there's a 25, whoops, that's not a very good radical. There's a 25 in there, and there's a 2 in there. What is the square root of 25? 5. So this square root of 50 can be written as 5 times the square root of 2. So what you're trying to do is pull out as much as you can out of that square root symbol. Let's do it. You try. You try. You try. You try. Square root of 27. See if you guys can come up with them. Morgan correctly said, whoa, what's that thing? That this is 3 root of 3. Okay? And where did that come from? This came from, you kind of think about it as factors, okay? It's that factors to the square root of 9 times the square root of 3, right? Because 9 times 3 gives you 27. And then she pulled out this 3 from the 9. So I could rewrite this as 3 root of 3. Okay? Yeah. And that's how you kind of do it. Okay? Now, unfortunately for you, it gets more tricky than this. Because sometimes I'll have ugly looking things like the square root of 45a cubed. And you go, oh my goodness, I don't know how to do that. Alright? So what you want to do is even variables, even letters, can be perfect squares. So I can rewrite this as, what perfect square is in 45? What perfect square is in 45? 9 times 5. So I'm going to write this as 9, square root of 9, times the square root of 5. What perfect square is in a cubed? Now, a isn't a perfect square, but a squared is a perfect square. Okay? And times a, because a squared times a gives you a cubed. See that? Okay? So now you pull out whatever you can out of these square root things. You try to get them outside of the box. Free them. Set them free. What's the square root of 9? 3. What's the square root of a squared? A. Okay? Because a times a will give you a squared. And then everything that you can't take out of the box, this and this, you leave inside the square root symbol. So that stays as 5a. So this simplifies to this. That's not an easy thing to do. So that's So you try to pull out, even when you have a variable, you try to pull out perfect squares. So here's a really hard one. Should I do a really hard one?
Yep.
Okay, I'm going to do that. 68 to the 7th. Let's even go further. 68 to the 7th, b to the 4th. Okay. Oh, square root of that. Square it. So you'll see some really ugly things that look like this. Okay. I can rewrite this, or I'm going to do it this way, and I can factor in things. Who knows what perfect square is in 60? What times what gives you 60? 10 times 6, but neither one of those, yes, but neither one of those is a perfect square. So you want to try to pull out a perfect square. 4 times what will give you 60? 15. So I want to pull out the perfect squares. There's a 4 in there, and there's a 15 in there. See? So that's one perfect square. And now I'm going to turn 8 to the 7th into, this is where you'll be a little bit confused, just a to the 6th, because 8 to the 6th is a perfect square, times, what's this square, times the square root of b to the 4th. This is one way to kind of think about it. You'll get faster as you work. What's the square root of 4? 2. This root of 15 has to stay, so I'm not going to worry about that yet. What's the square? Oops, I forgot about another a over here, okay? Because a to the 6 times a will give you a to the 7. So basically what you want to do is get these variables up to the highest even power. Because who knows what the square root of a to the 6 is? A to the what times a to the what will give you a to the 6? A to the 3, right? So you could pull this outside and turn it into a to the 3, because a to the 3 times a to the 3 gives you a to the 6. What's the square root of b to the 4th? B to the 2, okay, b to the 2nd. And then the stuff that you can't pull out, okay, has to stay in the box. So times the square root of 15a. So this thing here simplifies to this. And you say, how is that simpler? I don't know. It just is, you know, but that's what you're supposed to do with it. All right. Hopefully you won't get anything that brutal. I want to show you something else. Say I have a square root of 48. What can I break that into?
6 times.
What? 6 times 8. Okay, let's say I did decide that, well, neither 6 nor 8 are perfect squares. What number do you know goes into 48? Smaller than that. 7, not 7. 4. 4 times what?
12.
4 times 12. Okay? What's the square root of 4? 2. So I get a 2. But 12 has a perfect square in it too, right? What? It has a, no, not a perfect square.
3.
Yeah, it's got a root of 4 times a root of 3, right? And so you keep bringing these down. Remember, this is all multiplication. What's the square root of 4? 2 times the square root of 3. So what I end up getting is 2 times 2, which is 4, times the square root of 3. So this stays here. This turns into 2. And this stays. And then I multiply these together. And I came out with 4 root 3. Now, if you don't like all those steps, there's a bigger perfect square inside of 48. Does anyone know what that is? What's a big square number inside of 48? 16. 16. 16 times what? 3. Okay? This can be written as the square root of 16 times 3. The square root of 16 is what? What's the square root of 16? 4. So I could have done this problem in only one step if I pulled out the biggest perfect square. So whenever you can, try to recognize the biggest perfect square. Otherwise, you have to keep breaking it down like I did here. You see, I have to keep pulling out the biggest perfect square numbers. Okay? Unfortunately, we're not even close to done yet. It gets harder, Justin.
We need to do it, we have time to do one or two of these?
To do one or two of
Maybe
these?
you try,
You try.
just so they can.
Yes,
practice.
we do. Okay? Let's do a you try. Okay, here we go. You try. Square root of 20 x to the fourth y to the third. See if you can try to do that. Alright, see, this is definitely worth points if you get it right. Good. I got a pause. By step. Alright, so what does 20 break into? What does 20 break into? 4 and 5. That part's pretty easy, right? Hopefully on your test you won't get that much harder than that. Root of 4 times root of 5. What is, so x to the fourth is just x to the fourth, because that's a perfect square. And then I can take out a y squared out of that y cubed. Okay? This is n times the square root of y. So 4 times 5 gives me 20. Everything's still inside the square roots. Square root of x to the fourth, I'm just going to write it like that. Square root of y cubed, I'm writing as y squared times square root of y. So what is the square root of 4? 2. What is the square root of x to the fourth? X to the 2. Because x to the 2 times x to the 2 gives you x to the fourth. What's the square root of y squared? Y. And then these things you can't do anything with, so you leave it inside the box as 5y. And that's as far as you can go. That's their heart, okay? And they're confusing, but it is what it is. Alright? So what if I have something that looks like, ooh, this is hard. Okay? Here, boys. Let me show you this one. There's another one. So I have something that looks like this. 3 root of 2b times 4 root of 10b. You know what to do with that? So with multiplication, you don't have to do the distributive property, okay? You just multiply the numbers together and you multiply the square roots together. So the first step here would be to multiply the numbers together. 3 times 4 is what? 12. And 2 times 10 is 20. And that stays inside of the square root. And b times b is b squared. Okay? Now I try to break that down. All right? Ryan, pay attention. So now I'm going to try to break this down. 12, what perfect square is in 20? What times what? We just did this one. There's a 4 and there's a 5. And what is, let's just skip a step. What is the square root of b squared? B, right? And so now I have 12 times the square root of 4. What's the square root of 4? 2. 12 times 2, this is 2, right? Times the square root of 5 times b, because that's the square root of b squared. And then you don't want to write this b at the end, you want to write it at the beginning. You want to kind of put all your things outside of the square root in front of the square root symbol. So I multiply 12 times 2, which is what? 24. And I put the b in front of the radical, and I get 24 b root 5. So that's what that thing simplifies to right there. Okay? It's hard. I know. Okay. In the interest of time, I'm moving on to the next thing. Okay, Miss Lindgren?
God, there's more?
There's more. Yes.
That's why you need to have good examples written down right now. Hopefully you've been writing this stuff down.
Yeah. There's 2 more things that you gotta know. Okay? The next thing is division properties. So, property of square roots, just like with multiplication, division square root of a over b is equal to the square root of a over the square root of b. And what that allows us to do is solve problems like this. Square root of 16 over 25. This isn't too bad. So this is equal to the square root of 16 over the square root of 25. What's the square root of 16? 4. What's the square root of 25? 5. Okay? And keep telling me all the answers. Very good, Maureen. Okay? 4 out of 5. 4 over 5. Or you could just, you don't even have to do this step. You could just take the square root of 16 over the square root of 25. But sometimes, some of the things could come out of the square roots, and sometimes things can't come out of the square root. So say for example, I had this, square root of 11 over 49. I can rewrite this as the square root of 11 over the square root of 49. What is the square root of 11? Is it a perfect square? No, so you just leave that alone. But what is the square root of 49? 7. So you rewrite this as square root of 11 over 7. So if something can be pulled out of the square roots, you'll pull it out. Okay? One more type of thing you might see, and then we'll do a U-try. Say I have square root of 90 over 5. Okay? So I could do this like this. You don't know what the square root of 90 is, but I could break it apart into 9 and what? What could I break square root of 90 into? 9 times what gives you 90? 10. So I could do this. 9 square root of 9 times square root of 10 over square root of 5. What is the square root of 9? 3 root of 10 over the root of 5. But what I could have also done is done division. Did I do that right? Does 5 go into 90? Does it? Yeah, it must, right?
18 times.
18 times. Okay? Did I do something wrong? I could have done this. So these you could divide. So this gives you, sorry, up here, square root of 10 divided by square root of 5 is square root of 2, right? Square root of 2. But what I probably should have done is divided this by this and then rewritten this as the square root of 9 times the square root of 2, which is 3 root of 2.
Either way works.
Either way works.
A little more efficient the second way.
Should I tell them the math cheer yet? Do you know the math cheer? You don't know the math cheer? You ready to learn the math cheer, Jordan? Do we have any cheerleaders in here? Pom-poms? Okay, no recording me. Word. This is the math cheer. What?
But if they are involved in pop culture, I don't think they're willing to admit it quite yet.
Okay. You don't have to write this down, Yoselin. Okay?
This is the cheer.
This is the cheer. You haven't heard me do this before? Oh, you're in for a real treat. Okay? This is called the math cheer. Ready? How do you say this? No, but if you're kind of saying it fast, you say root of 2. Right? Root of 2. Okay, so you ready? You can say it along with me. Ready, set, and... No. Okay, here we go. It's on YouTube anyway. Here we go. How do you say this?
Root of 2.
Root of 2. So here we go together. Root of 2, 2. Root of 2, 2. Come on. Root of 2, root of 2, root of 2, 2. Root of 2, 2. Root of 2, 2. Root of 2, root of 2. Go, Matt, go!
I like it.
Yeah, thank you.
That's very
Okay.
good.
We can do that at the next. I learned that my first year of teaching from this old this old guy who has been teaching for it. It's one of my favorite things. Geometry, kids love me. You do it. If you do become a cheerleader, I expect that to be the cheer, right? The football game. Go math, go. All right, so the last thing we're going to learn about is called rationalizing denominators.
Take
Right?
good notes on this, people.
Okay, this is called rationalizing denominators. Denominators. Okay, rationalize denominators. Okay, and rationalizing, it should say. So say you have something like this, 3 over our new friend root of 2. Okay, root of 2. When I was in high school, we really didn't use calculators. You know, they were kind of a novelty. Okay, and this is a hard number to get a sense of. When I was in high school, the teacher said, memorize root of 2, memorize root of 3, get close to memorizing root of 5. And I still remember that this is about 1.414. You don't need to know that. And I still remember that this is about 1.732. And I still don't remember that this is about 2.2 something or something like that. Okay? The reason we rationalize denominators, because a lot of times you come up with answers with square roots in the denominator. And you want to get rid of the square root in the denominator because it's easier to get a sense of what that number is. For instance, 3 divided by the square root of 2. It's hard for me in my head to take 3 and divide it by 1.414. Okay? But if I rationalize it, and the way you rationalize it is by multiplying by 1. But you call 1 something funny. You call 1 root of 2 over root of 2. Okay? And so what happens when I multiply root of 2 times root of 2? What's root of 2 root of 2? Here again. What's root of 2 times root of 2? It's positive 2, because this is the root of 4. And so this turns into a 2 on the bottom. And on the top, I just leave it as 3 times root of 2. So in my head, I know that 3 over 2 is 1.5. So if I take 1.5 of 1.414, I could get pretty close to knowing that this is about that this expression is about 2.1. Okay, I don't know. I'm not going to make you estimate it, but I bet if you put this expression into your calculator, you would get very close to 2.1. Okay, so that's why we get rid of rationalizing denominators, because you want to, rationalizing means getting rid of the square root in the bottom. So let's do another one. Let's see if you could do one. Okay, 2 over the root of 5. Rationalize the denominator. It's not hard. Okay, you try. This quantity here is 1. You can divide anything by itself, and that's 1. And so essentially I'm multiplying by 1, so it doesn't change the value of this function. It just changes the value of this expression. So it just changes the way it looks. So root of 5 times root of 5 is plain old 5. And on the top, I just have my 2 root of 5. I don't know if I could do that in my head, but if I had to, 2 times 2.2 is about 4.4. Over 5, it's going to be somewhere like 0.8 or 0.9 or something like that. So I have an idea of what that number is. Okay? So anyway, that's, let me show you one more where they're going to get ugly on you again. Okay? Of course, as they always do. Last one. So square root of 7m over 10. And you say that doesn't look like anything. And they say rationalize. So I can rewrite this as a square root of 7m over the square root of 10. How do I get rid of that square root of 10 on the bottom? What do I multiply by? Melissa? Not by 10, by root of 10. Okay? So I'm going to get, because my goal is to get rid of this down here. Okay? So I multiply by root of 10 over root of 10. And when I do that, on the top, these square roots stay square roots. And so I get square root of 70m on the top. And what do I have on the bottom? What's root of 10 times root of 10? 10. And that's it. Okay? It's not that bad, is it? Okay. So, we're going to give you some chance to start your homework. You say,
Is there any like little list of things we could help them? Like, they could check
let me
in?
think about it after I give them the homework. Okay? So, page 581. 1 through 67. Don't whine and complain. Every other odd. Okay, that's only about 16 problems. It's not 67 problems. Every other odd. Okay? So what that means is 1 and 5 and 9 and what comes after that? 11, 13 until you get to 67. So you get kind of a smattering of all the different problems. And I think that the answers to these are in the back of the book. Okay? So, so you could check if you're doing them right. And that's the end. And remember, you heard it here.